Good morning, doctor. We are from Group 4B. Today we will present about our THERMOFLUID lab. So our title is 2-cup water flow experiment. Our group members consist of Fu Yuheng, Kwan Zheng Yip, Lo Yongxuan, Lim Yao Sheng, and Lim Yu Wei. So first I will present about the introduction about our project. So our experiment is about the orifice. Orifice is a small hole or opening that allows the fluid to flow through the opening. Orifice have many uses. It can be used to measure the flow rate, flow control, and to restrict the flow. Orifice reduce the area, and this will change the velocity and pressure. According to the Bernoulli's principle, the velocity of fluid will increase and the pressure will decrease when the area is reduced. This will create pressure difference and force the fluid flow from higher pressure to lower pressure. Greater pressure difference will have the greater flow rate. In this experiment, cup with hole used as the orifice in this experiment. So the water will flow from cup with higher position, which has the higher potential energy, to lower position cup. Next, we will continue to the theory part. So in this experiment, our calculation involve of two important equations which is important in fluid mechanics. That is Bernoulli's equation and the continuity equation. So the Bernoulli's equation is come from the Bernoulli's principle, and in this experiment we use it to calculate the velocity of flow. So Bernoulli's equation has three forms. First, energy form, second, head form, and third is pressure form. For the energy form, it is pressure energy plus kinetic energy plus potential energy equal to constant, and the head form, pressure head plus kinetic head plus potential head equal to constant. So for the pressure form, it is static pressure plus dynamic pressure plus hydrostatic pressure equal to constant. So in this experiment, our pressure one for the first cup and the second cup is 0 because it is open to the atmosphere and it is atmospheric pressure. And our velocity of fluid flow in first cup is 0 because it has the high surface area. So we get the velocity equation, which is v2 equal to square root of 2g bracket h1 minus h2. Next, we have continuity equation used to calculate the flow rate. Continuity equation has two types. It is incompressible and steady flow, which the density of fluid is constant and the density did not change during the flow. Next, compressible and steady flow, which the density of the fluid change when flow.
My name is Lim Yu Wei, and now I will explain about the apparatus for our experiment. For our apparatus, two transparent plastic cup is used in this experiment. A plastic straw is also used in this experiment. Other than that, we also use digital stopwatch to calculate the time taken for the water to flow. Fourth, we also use ruler to measure. 5. We also use a digital vernier caliper to calculate the diameter and the depth of the water. 6. A marker pen is also used to mark the initial height of the cup. 7. A measuring cylinder is used to measure the volume of the water. And 8. A standee or box is used so that one of the cup can be placed higher compared to the other one. Now let's move on to procedure of our experiment. Step 1. A plastic straw is inserted into one of the transparent plastic cup. Step 2. The cup is then marked for a different height, h1, using a marker pen with a gap of 10 mm each starting from an initial height of 46 mm. Step 3. The cup A with a straw is then placed above a raised platform. Step 4. The second cup, cup B, is then placed below cup A platform. Ensure both of the cups are aligned vertically to avoid spilling. Step 5. Cup A is then filled with water until it reaches 48 mm. A finger is pressed at the end of the straw when filling the water to prevent spillage. Step 6. Release the finger from the end of the straw to allow the water to flow from A to B, while starting the stopwatch to record the time of the water flow. Step 7. The stopwatch is then stopped when the water flow stopped. The time taken is then tabulated into our data list. Step 8. The water volume is then measured using a measuring cylinder, and the water volume V is then measured. Step 9. The experiment is then repeated from step 5 to 8, using different height with an increment of 10 mm from the first point for 5 more times. Step 10. All the data are tabulated.
So next I will present our experimental result. During the experiment, we record the data of initial height and the final height of the water in cup A. Then we also record the time taken for the water to flow out from the cup A. And lastly, the water volume flow out from the cup A. After that, we calculate the height difference and then the exit velocity. Next, the experimental calculation for the exit velocity of the water, V2, is calculated by using the formula of flow rate. Q dot equals to V over T, and Q dot is also equals to A times V2. Q dot is water flow rate, and capital V is the water volume flow out from the cup A. T is the time taken for the water to flow out, completely flow out. A is the cross-sectional area of the straw, and then V2 is the exit velocity. We equate two of these formula, and then finally we get V2 equals to V volume over area times time. So this is the cross-sectional calculation for cross-sectional area of the exit of the straw. During the experiment, first we measure the exit diameter of the straw, which is 6.6 millimeter, and then we put into the area formula to get the area value. Next, we also done for the theoretical result, which is by using the Bernoulli's equation to calculate the exit velocity V2. Before that, we do two assumptions, which is P1 equals to P2, due to the reason that both of the cup is open to the atmosphere, and then V1 is equal to 0, which is at the cup A, because the water decrease is too slow and can be negligible. So based on the assumption we have made in the previous slide, we simplify the Bernoulli's equation into this formula, which is V2 equals to square root 2g bracket h1 minus h2. So V2 is velocity of the water exiting the straw. G is the acceleration due to gravity, which the value is 9.81. H1 is the initial height of the water in cup A, and H2 is the final height of the water in cup A after the flow. So finally, we gather all the experimental data and the theoretical data of the exit velocity of water from the cup A and tabulate into as a table and do some comparison. And based on the data we have collected, we plotted a graph of the exit velocity, both of the experimental and theoretical data, against the trial number. We compare the trend of these two group of data. and the trend will be further discussed in the observation part.
In this part, I will talking about the observation in our experiment. So the key finding is the experimenter confirmed that as a height difference between H1 and H2 increases, both experimental and theoretical velocity increases, which is supporting the Bernoulli's principle. So the velocity of the water was influenced by the pressure difference due to the height difference, aligning with the hypothesis. The difference between the experimental and the theoretical velocity. So theoretical velocity were higher than the experimental velocity. This is because the difference was attributed to real-world factors not considered in Bernoulli's equation, such as the frictions and the turbulence when at a high flow rates. So this factor caused an energy loss, leading to lower observed velocity in the experiments. So the limitation of the experimental method is the friction and the turbulence was not controlled. So this will affecting the results, and the measurements of water volume and the time could have been more precise. And the external factor like temperature and air pressure could have influenced the results. In this part, we'll talk about the discussion for our experiments. So, increasing height difference between H1 and H2 lead to an increase in water velocity, which is consistent with Bernoulli's principles. So, as height difference increases, the time taken for the water to flow from cup A to cup B decreases, as greater gravitational force cause faster flow. So this experiment also highlight the practical challenge of applying theoretical fluid dynamics to real system, emphasizing the need to consider factors like resistance and flow in inefficiency in system designs. So the suggestions for improvement, so we have to use a larger diameter tube with smoother surface, or we have to use the automatic timing device and calibrate the measurements tools. Next, we also can vary the diameter of the straw, use liquid with different viscosity, and test with multiple cup heights and deeper inside. Or we can incorporate control airflow system to explore Bernoulli's principle with gases. And understanding the real-world derivation from theoretical prediction is crucial for engineering and scientists optimizing fluid system. The experiment reinforced the importance of bridging the gap between the theory and practice in solving practical engineering and scientific problems.
Hi, doctor. My name is Guan Jing Yip. Now we come to conclusion. So in our experiment, we demonstrated the relationship between high difference and water flow velocity, confirming Bernoulli's principle. As the high difference increased, so did the water's velocity while the flow time decreased. This support the idea that gravitational potential energy is converted into kinetic energy during the flow. However, there were discrepancies between theoretical and experimental results. Theoretical velocities were consistently higher because the calculation did not account for real-world factors like friction, turbulence, and energy losses in the system. These limitations highlight the challenge of applying idealized models to practical scenarios. So, despite these challenges, the experiment successfully illustrated Bernoulli's principle while emphasizing the importance of understanding real-world influences in fluid dynamics. Now we are in the part of recommendation. To improve accuracy in future experiments, we recommend using smoother and wider tubing to reduce friction and turbulence. More precise tools like automated timers and calibrated measure devices can also enhance data reliability. Expanding the experiment by testing different straw diameters, liquid viscosities, or varying cup highs could provide deeper insight into fluid behavior. Additionally, controlling external factors like temperature and pressure would reduce environmental impacts on the results. By refining the setup and exploring new variables, future experiments can bridge the gap between theory and practice, providing a more accurate understanding of fluid dynamics for real-world applications. That's all for our Group 4B presentation. Thank you.
这是4.6.6，所以现在重新做。